for the introduction. My name is Dimitrios Kosmas. I'm a PhD candidate at the NIFTY group, which stands for Nature-Inspired Fabrication and Transduction. We are part of the Robotics and Mechatronics group at the University of Twente in Netherlands. And my talk for today is about the development of a sensorized 3D printed pessary. And it's a work that is being held within the FITA project that is funded by NWO, the Dutch Research Foundation. So the typical structure for this talk, and I will start with background information, the necessary context. And the first thing that we need to know is pelvic organ prolapse, or POP for short, is a condition that describes the protrusion of the internal organs in the pelvic floor, or on the female pelvic floor, downwards. And it affects approximately 40% of the female population above 40 years old, especially with higher chances after childbirth. And the symptoms that are associated with that condition have the prospect, depending on the degree of how advanced the condition is, to significantly decrease the quality of life of women. The first line of treatment in this condition is what is called pessary treatment. Pessaries are basically a support device. It's a really old idea, but nowadays the modern pessaries are made out of compliant flexible silicone, and they're passive devices. They're inserted inside the body for support. The most common used shape is the one that's called the donut pessary. It's the one in the top right, or a pessary ring. They come in a variety of other sizes and shapes as well, but usually the first step is the donut one. It's the one that we also focus in this work. This treatment has a success quite high in a number that's approximately 60%. But the problem is that when that fails, the surgery might be necessary. And the degree of the success of the surgery is also not guaranteed. So it's associated with additional risk, rehabilitation time, and so on. And on top of that, the success mechanism of the pessary, so when the pessary works, or even when it doesn't work, it's uncertain as to what are the actual reasons behind that. So within the FITA project, there's the hypothesis that if we made tailor-made, like tailor-made to the individual pessaries, in a sense of a customized shape or a stiffness distribution that is safe to the individual, we might be able to increase the success rate of this treatment. But to do so, we need to understand the interaction of the pessary inside the body. We need to be able to judge the state of the pessary in the sense of what's the deformation of the pessary, what's the pressure distribution around the surface, and so on. And we have seen from, you can see from this MRI cross-section at the right, that from a perfect ring, the pessary in some situations deforms to a sort of an ellipsoid. So in this study, our approach was to start with a toroidal shape and explore the sensing possibilities if we're able to sense, to get a signal in a shear-loaded pessary, and we'll do so by employing multi-material fused filament fabrication, in this case for the additive manufacturing, and with conductive materials. So briefly about the method that we follow. As I briefly described, this is mostly an empirical approach, and we model the pessary after the dimensions of the conventional rings towards the smaller size. And we use multi-material fused filament fabrication, and we employ the piezo-resistive principle in this case to avoid challenges with shielding and so on. So you can see cross-section, a little bit of the design in the cut. You can see there is 4 strain gauges fully revolving around the ring. So that's basically a very simple symmetric placement across the circumference of the ring. This design is not aimed to be able to provide us with a localization as to where the pressure is applied. And the idea is to examine the response of these strain gauges and see what we can say about the exciting forces. Regarding the fabrication, we used a commercial machine. It's called the Abayazid series. Unfortunately, the company is no longer running, but this is a nice machine. It can print out 5 different materials. In this case, we only employ 2, which is 2 flexible materials. The first one, the CoexFlex X60, it's a 68 short hardness thermoplastic polyurethane. It's one of the softest materials that we can print with FFF. And the second one is also a TPU, doped with carbon particles, and it's the one that we use to realize the conductive structure. At the right, you can see one of the fabricated samples, along with a readout interface, which basically is attached with simple pins, some bridge readout, and the cables that are attached to the experimental setup. Very briefly, I will not stand a lot in this slide, but the idea is that Pessary is excited with a shear load by linear actuator, and we measure all the response over the strain gauges with a basic bridge readout circuit, and it's all based around the Duissoft 43s for the data acquisition system. And we also measure together the exciting force and the position of the piston. So, moving on to the results. Okay, first I will describe what we see. These two columns are basically different amplitudes. There was a series of experiments that was done from 1 up to 10 amplitudes in terms of harmonic characterization. And in the top, S1 and S2 are the sensors at the top and the bottom of the circumference, like the ones that are more sensitive to normal loads. And in the second plot are the sides. The S4 is the outer ring and the S3 is the inner ring. And in the bottom, you see basically the excitation is a force commanded experiment. So what we observe is a quite large settling time, a very low transient effect in the beginning. And we also observed, specifically in higher amplitudes, we see that there is this nonlinearity at the topic press. This is something that we have observed a lot in 3D printed piezoresistive sensors. One hypothesis as to the source of this effect is that there is this doped carbon that is in the carbon particles inside the polymer matrix that at very low strains they might be aligning, hence improving the conductivity, and then you continue to go into higher strains, you start breaking these connections apart and increasing the resistance again. Given the simple structure of the fully revolving strain gauges along the torus, and we're not stretching it a lot, so we know that basically the length, the total length does not change. So basically the net mechanical behavior that we expect from the strain gauges remains the same, despite the fact that we might have local compression and extension. So that makes it hard to make differential measurements, even if you use couples from the opposite sides of the neutral axis. And that results in the total in phase of the responses. Given that insight, we can choose then to only work on the best performing sensor out of all of these for shear loading. And that's the fourth sensor, the one that has the highest magnitude that we see. And in that case, you can see at the plot, at the left plot, that these are the average of all the cycles for each one of the experiments, this relative resistance change, in respect to the force that is applied. And it's clear that both the nonlinearity and the increasing hysteresis with amplitude, and that is quite hard of a signal to interpret and to calibrate. And this is where we took advantage of a work that we have presented previously in FLEPS of 2020, which about the compensation of model-based compensation methods for hysteresis. And this is basically a phenomenological model. There's a briefly description of the nonlinear state of the model on top. It's a network description. And for the specific extensions, we used the different sets for training and then another set for cross-validation. And we see that for this trained extension, we're able to get a satisfactory, much better estimation of the excited force. Especially if you focus on the region of the lower forces, which are more realizable within the pelvic floor. So finally, this is a summary, like the key takeaways out of this work. Is basically we're set out to understand how we can make a Pessary, or we can characterize the shear loads inside the pelvic floor. We design an experiment around it, and under harmonic excitations, we see that all gates exhibit like in-phase drifting and nonlinear response. That in this simple design, differential measurement, which helps in minimizing these nonlinearities, is not beneficial because all the responses were in phase. And we saw that we were able to partially compensate for creep and hysteresis by using model-based compensation techniques. And that is all. Thank you.